Hi, in this video, we're going to talk about hash function for strings. So as we mentioned, oftentimes we want to hash strings because we want to look up by, let's say, names. So how do we transform strings into integers? Well, we kind of learn it can be done with an idea like the ASCII, right? And even without using ASCII exactly as it is, we can kind of imagine having a mapping table. Let's say that maps a letter into a number, A into 1, B into 2, C into 3, and so on. And then for a string that consists of multiple of such letters, then we will map each letter into a number, and then perhaps at the end add all the numbers up. So an example like this would be the word R. A maps to 1, R maps to 18, 5 maps to E maps to 5. We sum them up, have a 24. That could be our hash for this string. Now, is this a good hash function? Well, as it turns out, it's terrible. So the biggest problem with this is that it does not take into account the position of a letter. So, for example, anagrams, and anagrams are just strings or words with the same letters but rearranged. So the word R, era, and ear, they all have the letter E, A, and R, and all of these will just hash into the same value. So you're going to have lots of collisions, and also even outside of anagrams, lots of different words can hash into the same value. If you don't believe me, try the word fried and hot, and and then also words with similar length, they tend to kind of when you hash them using this hash function, they tend to be clustered together, and there are other problems with it. But to show you this is a graph that I dig up, and somebody basically take uh, all the words from an English language dictionary, hash them using the scheme we just talked about, and then these are all the possible hash values. We start, the smallest one is 0 for the letter A, and then some very large hash values. But if you look at the frequencies or the number of occurrences of each of these hash values, you can kind of see, the number around 100 happens a lot. There are almost 2,000 of them. And then, these other values around it, there's still, there are a lot of words that, when hashed, their hash value kind of cluster around um, this 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 value. And that's understandable, right? Most English words are probably, I don't know, 4 or 5 letters long. And they're, if you add all of them up, they kind of end up in the same general sum in this table. So if you actually want more information about this study, I have a link down here. It's a kind of a fun read, but it gives you a deeper understanding of hashing strings. Anyway, so if that's a bad hash function for strings, what's a better one? Well, a better one would try to distribute the hash values more evenly. Okay, one way, there are different ways to do this. One way is using radixes. And to understand how it works, let's just look at how numbers are written. So the system that we're most familiar with, the decimal numbers, let's say the number 4,821, they are effectively the number 4 times 10 raised to the third power, 8 times 10 raised to the second power, 2 times 10 raised to the first power, and then plus 1, right? So the radix in this case is 10, right? And that's what decimal system uses. Other in computer science, you probably have seen, the hex system that use the radix 16, and then the binary system obviously use the radix of 2. We can apply the same idea to strings. And so what it is, in order to hash the word A-R-E, we take it because that's, we start at the least significant uh, uh, place or the word at the end. So this could be, radix, whatever radix, we pick a radix, we'll pick a radix, raised to the 0 power, radix to the radix, raised to first power, second power, and so on and so forth. So, and we add all of it, kind of just add it up, right? We add the products up at the end. So this solves the problem of anagram, right? You should be able to see why it solves the problem of anagram, and also it creates a much larger number, meaning the hash values is going to be spread over a wider range of numbers. So that's good. So what the radix is usually some prime numbers, and the Java actually use the radix 31. So the more general hash function for strings actually looks something like this. We just replace this is for kind of arbitrary long string. Okay. Now, if you look at this, there are a lot of things raising to the power, raising 31 to the n minus power. What if n is 100, right? A string with 100 characters. So this could be very, very expensive to compute. However, the computation can be optimized, and that is by observing that this expression is actually the same as this other expression. And what this expression is saying is that the hash of a string is the hash of just the last letter plus 10 times the hash of the string minus the last letter. Okay, so if you want more details, the reading has, I think, a slightly more detailed explanation of this. But if you believe that, then what we can actually end up writing a hash string function that looks like this, that use only a single multiplication each step, rather than 31 raised to a particular power. Now these two should produce exactly the same result, and I actually already have them defined here. This is the slow one that use power, and this is the fast one. And if we run them and compare the results, both of them hash to exactly the same values. Okay, so I just alluded to, Java's string hash actually used the radix 31. I think the reading actually says 37. I think that's a fairly old version of Java. I believe the later ones use 31, although I haven't looked at like the latest one. Does it still keep 31? Anyway, this is a bunch of documentation that support my claim. This is the Java doc, and this is actually a bug report that changes radix 37 to 31. And then when we come to Python actually use a very interesting radix, and that is this number. And if you want proof, go to the source Python source, and that's actually written in C. The search for the string hash, and you'll see this prime number. And now, having said that, that's one way to do hashing. I only said it was a better hashing function for strings. The best ones are really what's called the cryptographic hash functions. You might have heard of them before, such as MD5 or SHA-1, etc. So their hash output is huge, hundreds of bits, and pretty much it's almost guaranteed that they have no collisions. And then obviously they have many applications outside of hash tables, such as for signing messages. And they are actually available in Python through the hash lib modules. But then why don't we just use them all the time? The problem is it takes a lot of computational power to compute them. So and for most applications, the string function, the string hash function that I just demonstrated, that was good enough. And then lastly, I just want to point out that given the nature of hash functions, right? It's trying to distribute values all over the place. They're kind of random or pseudo random. So items in a hash table, they are totally unordered. So if we were ever to iterate through our hash table, the order of items, that they will be nothing like the order in which we insert those items.